talk is Jason Hartline, talking about truth or envy.
Thanks, Hannah. Okay, so this is joint work with Chi-Chi Yan, who's a PhD student with Tim Roughgarden at Stanford. Good, so I'm going to be talking about truth or envy, and this is work towards a theory for prior-free mechanism design. And I guess I want to say before I get started that I am a big supporter of something that Eva said during the panel, which is computer science theorists, when they started working on mechanism design, had focused very strongly on prior-free mechanism design because that's what we knew how to do, and that's what we've done before, and that's what made the most sense to us. And I think it's really important that we be a lot more open-minded and explore a lot more kinds of solution concepts in the future work that we do in this area. So this talk is not going to emphasize that feeling I have, which is why I wanted to say it before starting. That said, I think that the work that we have done in prior-free mechanism has been very important, and this bias that we had starting out has led to a lot of really interesting results, and hopefully I'll convince you that the one I'm going to present today is one of those such interesting results. Okay, so truth or envy. So I'm first going to tell you what I mean by truth, and actually you guys all know, but I want to say a few things about it. Okay, so I'm talking about mechanism design, which is how a social planner can achieve a desired objective when participants' preferences are private. The main challenge is he doesn't know the preferences, and the agents may strategize when reporting them. That doesn't often happen. Talks. The main definition that is a starting point for a lot of this work is incentive compatibility. And a mechanism is incentive compatible if, and I'm going to use the loosest possible definition, is if truthful reporting is in equilibrium, meaning given that other agents report truthfully, an agent maximizes her utility by reporting truthfully. And the main thing I want to point out here is, okay, so our goal for this talk, I'm going to focus on a particular objective, which is profit. I don't actually care about the objective too much, and I hope that you'll take this talk and apply the techniques to any objective that you like a lot better than profit, but I'm going to just use it as an example here. So we'd like to design incentive-compatible mechanisms with good performance. Okay, and the main complication that, that is introduced by incentive compatibility, which is what's driving the additional hardness results that Shahar was talking about in coming up with the algorithm is easy, but now you've added some incentive constraints. Okay? And the main complication is that incentive constraints bind across all preference profiles. And so, whereas before in algorithm design, you usually have an input and you just want to do something that's okay for that input. And there's one input that you care about. Whereas in mechanism design, because the IC constraints bind across all valuation profiles, and that's because an agent cares what happens on a misreport that they might make, and that's a different valuation profile. That's another input to the algorithm. So that constraint takes one problem of optimizing for one input and turns into a problem of optimizing simultaneously over all inputs to get a mechanism. And that makes the problem a lot more complicated. So that's the main challenge introduced by incentive compatibility. And so some consequences of this challenge are the following. No mechanism is going to be optimal for all preference profiles. Okay? You're optimizing across all preference profiles simultaneously, and so you're going to be inherently trading off your performance on one profile for another profile. Okay? And if you have a prior distribution, meaning if I tell you the probability that each profile arrives, then you can exactly know how to trade off this profile. You can do what Costas mentioned in the first talk. You write the big LP, which has a probability distribution for each profile that shows up, and you trade off that revenue you get. Okay? Good, so I want to give you an example of that in one of the most simple settings possible, just to make sure we're on the same page. So if you were selling k units of an item, so this is in Shahar's language is a multi-unit auction, and n agents with values drawn, n unit demand agents who want one of these items, values drawn IID from uniform 0, 1, then I can say, well, what, here's my distributional assumption. I can say, now, what auction maximizes the seller's profit under this distributional assumption? Okay, and you can optimize it, and Roger Meyerson did, and he told us that the optimal auction in this setting is the k item Vickery auction with reserve price 1/2. Okay, and the next thing you can ask, well, what if we change this distribution to something else, say exponential with rate 1? So I changed the distribution, and now I need to re-optimize across all valuation profiles the auction I want, and I get a different auction. Okay, it's the k item Vickery auction with reserve price 1. Okay, so as you can see, if I want to maximize my expected revenue, I do need to certainly trade off the revenue across different profiles, and importantly, the optimal auction does depend on the prior distribution that we have coming in. Okay, so now I want to make some complaints about this approach of mechanism design. And I'm not going to make these complaints with the assumption that, and to say that we shouldn't be doing Bayesian mechanism design, because we absolutely should. And this stuff, these optimal mechanism designs are very, very important. And in fact, they're important for what I want to tell you. They're sort of a first step. Okay? But let me complain about priors. So the first complaint is, where did the prior come from? Where did you, a mechanism designer wants to design a mechanism for a situation. And so, okay, here's a mechanism, right, that depends on the prior. Oh, where do I get my prior from? Okay, you could do market analysis. You could look at past sales. There's some problems with these things. So suppose you look at your experience in the market, past transactions for getting your prior. This is going to be problematic because of the fact that, well, if you have agents you're repeatedly interacting with, then they're going to know that you're going to use their past actions against them in the future, and they're going to possibly manipulate what they did previously for you. So you've got to be careful using historical information in your auction to inform what you're going to do in the future, because then you'll get some coast conjecture kind of results where the only thing you can do is the efficient allocation. Okay? The other big issue I have is the prior accurate? And here's the point of view. Let's suppose I was selling supercomputers. Okay, supercomputers, how many people want supercomputers? Or how many institutions want supercomputers? Maybe 5. Okay, so there are 5 potential people in the market for supercomputers. And usually when you do Bayesian mechanism design, you assume a continuously differentiable prior distribution, which you get from sampling an infinite number of players. And so somehow my assumption was that I had an infinite number of players coming in, or that I could sample from to get an arbitrary accurate prior distribution. And then I use this to sell to these 5 players. But I only have 5 players in my market period in the world. How could I ever have sampled an infinite number of players? Right, so there's this asymmetry in the assumption of you have 5 players, you sampled an infinite number of them. That's ridiculous. Right? Somehow, fundamentally, you should be tying the accuracy of your prior to the size of your market. And that's not happening if you just assume you have a continuous prior in the first place. Okay, so that's another complaint. Another complaint, which is also related to something called the Wilson doctrine, is that prior dependent mechanisms are non-robust. You give me a mechanism that is optimal for some distribution, maybe that mechanism picked out something very specific about this distribution, and if you generalize even a little bit from this distribution, it's going to be terrible. Okay, and so there's some serious non-robustness with prior dependent mechanisms, especially when you go to correlated settings. Okay, and the last point actually is the one that I think is probably the most important. And this is one of the reasons why I think computer scientists have been so drawn for a long time to mechanisms or algorithms that don't assume anything about the distribution is that what if we want one mechanism to be used in many different scenarios, and we don't really know what those scenarios might be? For instance, when we deployed the TCP/IP routing protocol in the internet, we had no clue 40 years later what it would be used for video on demand, all the stuff that we do today with the internet, right? And it works fairly well for all these workloads that the designers had no clue about. And so we like that. That makes it a protocol a lot more useful and a lot more important. Okay, so that's my final point. So given these motivations, I want to talk about developing a theory for prior free mechanism design that goes beyond the sort of starting point of the Bayesian mechanism design point of view. And I think this is one of the main contributions to algorithmic game theory to the general game theory economics point of view, is that we started out with this bias towards prior free that made us do certain things that people weren't thinking about, and I think that's useful and important. Okay, so that's what I meant by incentives and the problems therein. I want to now tell you what I mean by MB. So here is a multi-unit pricing problem, very similar to the auction problem I put up earlier. So I have n agents with values which I'll just sort, v1 through vn, k units of an item. And I would like to come up with the MB-free revenue maximizing pricing, meaning I want to price these items for these agents in a way that there's no MB. Okay, so what's the first thing you might think about doing in coming up with an MB-free pricing of these items? Well, MB-free, well, it means if I'm going to sell items to the same people, I better use the same price, right? So I can think about selling at price VI. And of course, if I sell at price VI, well, then all the top I players, the players with values above VI, are going to want to buy at price VI. And everyone below VI is not going to want to buy. So my revenue there is I times VI. I'm going to call that R of I throughout the entire lecture. And then, if I wanted to maximize my MB-free pricing, well, the first thing you might say is, well, just pick J to maximize the argmax of Ri. Okay? Good. So I call this a pricing because, essentially, I mean, I can think of it in terms of who I allocate to and what price I sell to them at, but I can also think of it just, well, we're just pricing the item. And the item is priced at VI, and people who want it take it, otherwise people don't take it. Absolutely not. This is a unit demand setting. Agents are buying an item. Okay? Okay, so I want to make this example really specific so we can see exactly what's going on with a picture. So suppose I have 20 units of item for sale, 90 interested agents. 10 of them are high-valued agents with value 10, and the other 80 are low-valued agents with value 2. Okay, so I want to draw this with a picture. So let's draw this function R of I, meaning the revenue I get for selling I items. And so as I sell more items, my revenue increases with a slope of 10 until I sell the 11th item, which I have to sell at price 2, and my revenue drops to 22. It thereafter increases at a rate of 2 up to 180 for selling 90 items total. Okay, now I only have 20 items, so I could maximize Ri in this region, which of course is going to pick this point with a revenue of 100. And so my first question here in exploring MB-free pricing is, can we do better than this? Okay, so here's my example. And the thing I want you to think about when considering whether you can do better is, what if we tried to use randomization here? So before, these prices were just deterministic. I price the item, but maybe I could do something better using randomization. And here's an idea. So let's sell to all the high-valued agents at price 9. And let's sell to the 2 valued agents with probability 1/8 each. In other words, there are 80 of them, so I'll sell to 10 of them, the remaining 10 of them, at price 2. So if I did this, My revenue would be what? Well, it would be 9 times each of the 10 agents and 2 times each of the low agents that I sell to, and the revenue would be 110, if I could do this. Okay, well now let's investigate envy. That's correct. So I'm going to implement this by picking 10 of the low agents at random. That's correct.
And what's the precise definition of envy?
I'm going to get there. Okay? But for this discussion, we'll assume it's ex ante envy.
Before getting the
It's
valuation.
before getting, sorry. It's interim. It's
After getting the valuation.
you have your value, but you don't know whether I'm going to serve you or not.
So I cannot envy someone who has a different value than mine.
You can envy someone who has a different value than you.
Okay, so that's why I want to see the definition. Okay.
We'll get there. So what is, I want to say, why is this envy free? This will help your question. Why is this envy free? So let's look at a player with value 10. They have 2 choices. They could, as I've suggested, take the item at price 9 always and have utility 1. What's their other option? Well, they could try to get the same treatment as the lower valued player, right? What's the same treatment of the lower valued player? Well, they win with probability 1/8, because that's the probability the low probability is selected. And if they win, they pay 2. So their utility is 10 minus 2 when they win, but they win with probability 1/8, and 10 minus 2 is 8, times 1/8 is 1. Okay?
It's not exactly 1/8 once 10 becomes a 2.
That's incorrect, and that's the main point about envy. Because I'm asking whether someone envies another player. Does the 10 envy a 2? He doesn't deviate. He doesn't change his value. It says, does he envy the 2 player? And thank you for asking that question, because that's a very important distinction, which we'll get to in a second.
Previous mechanism therefore was not envy-free.
Excuse me?
Which means that the fixed price was not envy-free.
It was envy-free.
Mr. 2 envied Mr. 10, right?
No, because the 10 was paying 10.
Fixed price at 10, so it was to pay 9 or 10.
Right? And it's obvious the 2 isn't envious. The 2 doesn't want to pay 9. And they're happy to win with probably 1/8 and pay 2 and get utility 0. Okay, this is envy-free. Yes. What revenue does this get? This gets revenue 110, which I've drawn here on the convex hull of the original revenue curve. Okay, it is exactly the point on the convex hull. That is not a coincidence. We'll see why this is in a second. Okay, so what's the definition of envy-free? Pricing is envy-free if no agent wants to swap outcomes and payments with some other agent. Meaning I look at what other agent gets. Do I want what they got instead of what I got? Okay, I don't care that they might have a high utility for that because their value is higher than mine. What I care is what they got from the mechanism. Okay, and I want to point out the main simplification that Sergio pointed out for me of envy-freeness, which is that envy-freeness constrains what the mechanism can do point-wise on the particular valuation profile, and I don't care what would happen on some other valuation profile where someone potentially might have changed their value to something else. It's only defined point-wise, because we're not asking what happens when someone changes their value. We're asking what happens when they sort of just take someone else's outcome. Okay, if that were possible. That's not possible, but what if it were? That's what envy is talking about. Okay, so over incentive compatibility, we now have a point-wise constraint on the valuation profiles, which now makes things a lot simpler. And so consequentially, for any objective you might have, there is a envy-free optimal pricing. There's some pricing that optimizes that objective, because you optimize point-wise on that profile. Okay, good. So that's my introduction. What's truth? What's envy? The main point of my talk is that incentive compatibility and envy-freeness are really almost the same thing. And because they're almost the same thing, if you want a good theory for prior free mechanism design, NV freeness is inherently prior free, and it's maybe something that's very important for us to be thinking about. Okay? And I want to make some comments on related work, which is exactly what Sergio was mumbling. If you take the limit of as the number of players going to infinity, then they're identical. They're the exact same thing. This is a paper by Jackson and Kremer in 07.
For what settings?
For what settings? I'm not sure I care. Probably all settings you care about, you can prove a theorem kind of like this. Essentially, as the agents become small, then their deviations don't even matter, right? And it's like they just were able to take some other person's outcome instead of deviating. Okay, so good. So that's that.
This is like in the distributional context, right?
Excuse me?
This is in a IID context or something?
Sure. Okay, so I want to, along the idea that NV freeness is something we should care about, there's a paper I really like by Day and Milgram, which says that in combinatorial auctions, you might prefer over incentive compatibility to have another property, which is a core allocation, which is some kind of stability property of the outcome of the mechanism. And that may be, so core and incentive compatibility are impossible together, and you may prefer something like core over something like incentive compatibility if you had to choose. Okay? I'm not going to take the point of advocating for NV freeness over incentive compatibility. Okay? I'm going to take the point of NV freeness should really guide the design of incentive compatible mechanisms, which is a different point of view. Okay? Another related paper is this paper by Azevedo and Budish, which says, related to this, the second paper on the core allocation, says that incentive compatibility for price takers maybe is the condition we want. And so this paper looks at two different kinds of incentive compatibility violations you could consider. You could look at incentive compatibility violations, which are sort of the opposite of what Shahar was saying. It means it's not, it violates the taxation principle. I ask someone what their favorite item is, and they say, I like item A over item B. And you say, OK, well, here's item B. And that's your mechanism. You give them whatever one they like least. This is obviously not going to be incentive compatible no matter what, not even in the limit, not anything, right? Because you just took what they did and did the wrong thing. And so something that's incentive compatible for price takers, meaning when the agents get small in the limit, is the limit result, is probably the important thing. So if there is a menu that they're picking off of, but maybe their bid subtly affects the menu, well, that's more incentive compatible than the thing where there isn't even a menu that's the right thing. Okay? I think these are important directions. That's not my point. And for instance, I really care about the small n case. In the large n case, I might as well assume I have remember my example, my motivation in the beginning. I said, if I had 5 players, right, where do I get this infinitely accurate prior? Well, if I have an infinite number of players, of course I can get an infinitely accurate prior. That's fine. It's no big deal. So I don't care about the infinite case at all. Actually, I should assume this IC equals EF result just because I could get a prior if I wanted, right? So I think the small n case is really the interesting case. So my thesis actually is NV freedom is approximately equal to incentive compatibility, and not just in the limit, actually for all n. Okay? And my goal is to come up with approximately optimal NV-free, my goal is to approximate the optimal NV-free pricing with an incentive compatible mechanism. Okay, so somehow, because they're similar, the constraints are similar, and now if I can show, even in the small n case, that I can approximate this thing that is not incentive compatible with something incentive compatible, it says that even more so, this NV-free thing is the right thing to be thinking about in terms of what you can do with incentive compatible mechanisms. Okay? Okay, so here's an overview of the talk. I've got 10 minutes left, which is fine. Yes?
I'm just curious about the advantages of the NV-free mechanisms. I mean, assuming that they're close to the revenue that you'd be able to get with incentive compatibility. compatibility.
Mm-hmm.
I mean, if so computationally, there are no issues here, right? So what are kind of the, I mean, aside from the fact that
Let me just give the talk and ask it again if you still have that question. Okay, so here's what I'm going to do. I'm first going to characterize and optimize envy-free prices, and you'll see from this characterization and optimization that I do that structurally these things are very close. Okay, I'm then going to talk about revenue that I get. I'm going to fix a mechanism and talk about revenue, and I'm going to say, well, actually, the envy-free revenue of that mechanism, which is not the same as the IC revenue, and the IC revenue of that mechanism are close. And we'll see that later. And then we'll talk about designing prior-free mechanisms that approximate these. Okay, so what do I mean by envy-freeness? Let's get some notation. So I had values v1 through vn. I'll have an outcome x, where xi is the probability that agent I is served. I'll have payments p, where pi is the expected payment of the agent. The utility agent is vi xi minus pi. Okay, I'm going to assume all the agents are risk neutral, and this is what they're trying to optimize. And our profit is obviously the sum of the payments. Okay? Good. So I now want to characterize and optimize envy-free pricings. Okay, so my values are increasing. What's the envy-free constraint say? It says that agent I's utility, which is the value times their probability of winning minus their payment, is bigger than the utility they would have if they took agent J's probability of winning and payment. Okay? For those of you who've looked at IC mechanism design, this looks very much like an IC constraint. You can prove in the same way this theorem, which is that envy-freeness implies monotonicity, meaning agents with higher values must receive the output with no lower probabilities than agents with lower values. So I could plot the values on the x-axis and the probabilities of winning on the y-axis and get some sort of increasing looking set of dots. Okay? Let's take the smallest monotone function that's consistent with these set of dots, so the lower stair. There I've drawn it. Okay, so the payments that are envy-free that have this allocation are the area above this curve. So if I have my value right here, it would be this orange thing. And so depending on your value, you pay the area above that curve. Okay, these are for the maximum envy-free payments. So this characterizes allocations and the payments that have to go along with that. I then, as I defined earlier in the talk about this revenue curve, this I times VI. This is the revenue I get from selling to I things. And I can talk about its derivative. In other words, the difference between two consecutive points in the revenue curve. And I call that the virtual value, following Meyerson's construction for optimal mechanism design. And then you can prove the following theorem by using this payment characterization, that the revenue you get from the mechanism is exactly equal to the virtual surplus of the mechanism, the sum, the virtual values times the probability of serving. Okay, that's exactly equal to your revenue. Okay? Which means if I'm trying to optimize my pricing, what's the optimal pricing? Well, it's to maximize virtual values subject to whatever feasibility constraint I had as a designer and monotonicity constraint that these things are increasing. Okay? And then you do the natural thing to get rid of the monotonicity constraint. You take your revenue curve, you take the convex hull of it, you iron it, in other words. Define new virtual values to be the derivative of that. Well, these new virtual values are always monotonically decreasing, meaning that higher values are higher virtual values. Okay, and so if you optimize a monotonically decreasing function subject to feasibility, it'll turn out to be monotone for free. So you can drop the monotonicity constraint. And then the optimal pricing is just to maximize iron virtual values subject to feasibility and using random tie breaking. That is what envy-free optimal mechanisms are for single parameter settings. That's it. And for those of you who are familiar with incentive-compatible mechanism design, you've seen all this before, because that's the picture for incentive compatibility. This is due to Roger Meyerson and Bulot and Roberts, where instead of having an input, this is sort of the empirical distribution. This is the actual values that I got. This is I just used the Bayesian probability distribution instead. And then your IC characterization allows deviations instead of swaps. And then you get the exact same theorem. Okay? Good. So you can make thanks. You can make a comparison between optimal IC mechanisms for a Bayesian prior and optimal MV-free pricings. And optimal IC mechanisms are based on the prior distribution, whereas optimal MV-free prices are based on the empirical distribution, meaning the actual values that showed up. Okay, but other than that, they're the same thing. I want to give you a quick example, which is coming from settings of sponsored search. So position auctions, you have a bunch of slots that get clicked on with decreasing probabilities. I want to assign agents to these slots. Good, so what's the revenue maximizing pricing? Well, it's easy. You just calculate the revenue curve for the values you have. You take the concave hull of it, and you assign the agents to positions greedily by their iron virtual value, breaking ties randomly. So if some agents have the same virtual value, I randomly permute them, but otherwise I go greedily down the order of virtual values. The revenue you get from this, you can read right off the revenue curve, looking at the differences in the derivative, essentially. And it's just the iron virtual values times the weights of the agents in the clicked weights. That's exactly what it is. Okay? All that matters, of course, is the partial order on the virtual values. Okay? I now want to talk about comparing the revenue in these two settings. And so I now want to come back to what Sergio was complaining about, was if someone, compared to the IC versus MV-free, if someone deviates, things change slightly. Okay, and so I now want to say what that means. So look at the MV-free example. Again, 20 units, 10 high bidders, 80 low bidders. And the proposed mechanism is to allocate items to all high bidders and remaining items to low bidders at random. That's what I'm going to do. So if I do this mechanism, what is my allocation rule? Well, the low bidders win with probability 1/8, the high bidders win with probability 1, so I get these 2 points. The payments come from the lower stair, so I get this payment of 1/4 for the low players and 9 for the high players. That's exactly, 1/4 was actually is 2 times 1/8, right? The probability they win. So it's the same thing I had before, and my revenue is 110. Okay? What if I have incentive compatibility with the same mechanism? Well, incentive compatibility, the constraints on keeping you from deviating are slightly different from the MV-free constraints because you're not swapping, you're unilaterally deviating. So that's going to induce different payments. So how do those payments differ? How is the revenue of the same mechanism different? Okay, so what are the allocation rules? Well, we have the allocation rule for a low player. Well, with probability 1/8 they win, and if they're a low player. And the high player, they'll win if the low player deviates to be a high player, well, then they'll also win always. Right? So the low player, if they bid low, they win with probably 1/8, and if they deviate to a high, they win always. A high player, the situation is different. They're going to win always, but if they deviate to a low player, to low value, then they're going to win. Well, there were 10 items sold to high players, but if they deviate, there are now only 9 items sold to high players. So there are 11 remaining items and 81 low players, and so this is 11 over 81, which is slightly higher than this curve. Okay, so you can calculate the payments as before, and you'll get that these are slightly different. Your revenue is 109 instead of 110, if you look at the IC payments for the same mechanism. Okay, so the revenues are approximately the same for the same allocation rule. And so that actually is a quite general theorem, which you can write here. And in interest of time, I'm not going to tell you exactly what I mean by this. But essentially, point-wise, for any valuation profile, your MV-free revenue is at least the IC revenue, which is at least the MV-free revenue over 2. So these are all always close to each other. That's really nice. I'm not going to tell you the caveats. And I'm now going to tell you how you can get prior-free mechanisms from this. Okay? So here's my sketch. And the thing that I like about this is we get it sort of entirely from reduction from a very simple setting which we understand very well. So the digital goods setting is somehow very simple because there's no supply constraints. It's just how do you price. And you can essentially use the empirical distribution to price well and get a beta approximation. And then you can go to multi-unit auctions losing a factor of 2. And that's basically the difference between these lotteries versus the deterministic RI. So these bumpy curve versus the convex hull is a factor of 2. then you can get all the way to position auctions and matroid permutation auctions just by reduction. Okay? And this is because structurally, these things are very closely related. And the result, I think, is very nice, is that you can also get all the way down to downward closed permutation settings and getting constant approximations using this fact that NV-free and IC revenue are very close. Okay, and so essentially what you can do is analyze the NV-free revenue of a mechanism up until the very last point. And then you say, well, its IC revenue has to be close to its NV-free revenue. And its NV-free revenue is defined point-wise, and its IC revenue is hard to define. So that is a nice structural simplification. Okay, I'm going to skip the rationale for all of this and tell you what my conclusions are. So I've talked about NV-free pricing for single parameter settings. There's a very close connection between NV-free pricing and Bayesian mechanism design. So it's not that we shouldn't do Bayesian mechanism design, you should do it. Now you can maybe do that just in the context of doing these NV-free prices and get the exact same structural results. So you're studying basically the same concept. And it's a simpler setting, so it might yield tractable results for problems where IC analysis was a lot harder. And in some sense, these NV-free prices give the right benchmark for IC approximation. If you want to design and set incompatible mechanisms that approximate that are good in general, approximating the NV-free benchmark is probably the right thing to do. Okay, thanks.
I still have a feeling that your approximation is mainly for large n, and not for small n. So how good is that? I mean, look, if there is one buyer, I mean, clearly NV-free means nothing. Okay? So if you have two buyers, then there is only one other. So these conditions must be extremely weak. So somehow you need enough people there to get some mileage.
Yeah, the answer is 2.
2 people, you mean?
Yes.
Oh, but you have a thing. Oh, sorry. Everything is in one good, right?
No, I have arbitrary feasibility constraints. The answer is 2 people.
You are selling M goods to people. You say NV-free and incentive compatible are closed in a factor of 2.
Yeah.
Okay.
Incentive compatible is not going to bite much either.
Oh, it's going to bite a lot. It's going to bite a lot. Even for one person, it's going to bite a lot.
So here's the thing. So NV-freeness, you're right, says nothing with one player, because for one player, I can just charge him his value. That's the only thing I have to worry about. Okay, as soon as there are other players where I might want to charge, if I don't want to just charge the highest bidder his value, then that's the only case I have to worry about. That, in this literature on prior free mechanism design, that case is seen as a technicality that you just kind of ignore, but there are ways to make it precise. Yes?
So what if I say, mechanism design is too hard, I'm just going to do NV-free optimal pricing and run that as my mechanism. It's not going to be incentive compatible, but maybe so it seems like in the randomized setting, maybe it's very, there's only so much incentive to deviate. Can you say something about with sufficient bidders? If it's
That's exactly what those prior, the related work that I mentioned to you, which shows that things get close in the limit. They actually approach the limit pretty quickly. And so...
but it can't be a completely universal state, right? Because in the deterministic case, with the guys who have value 10 and the guys who have value 2, you might have lots and lots of those guys, but if it's close to the boundary, one guy switches from 10 to 2 and just decides, and thereby moves the price from 10 to 2. So then there is still a big, so I'm trying to get some sense of what the conditions are.
No, he doesn't move the price from 10 to 2.
In the deterministic setting.
Oh,
Has to be the 2.
you don't want to look at the deterministic setting. So I want to. So this is a good point here. So the issue there are certainly issues between deterministic and randomized mechanisms, and in some sense, restricting to deterministic mechanisms can hurt you a lot in 2 ways. They can hurt you a lot in performance, but they can also hurt you a lot in sort of structural simplification of the problem. And I think it's hugely problematic to restrict your attention to deterministic questions when that makes the problem much, much more complicated and conceptually more difficult to understand, because in sort of in understanding what incentives do, you're already making an assumption of the revelation principle, which is there was some equilibrium you wanted in some mechanism, which maybe wasn't a direct revelation mechanism. Maybe people were playing mixed strategies, whatever. So it was a determinist mechanism with mixed strategies. So I should assume randomization probably anyway, and especially if not assuming it hurts me a lot, I should definitely assume randomization is fine.
So I agree with many of those points, but I would encourage us to work on deterministic mechanisms.
We already have a lot.
Yeah, no, I agree.
Okay, last question.
How important is it to be single-dimensional rather than, let's say, low-dimensional?
That would be a great question for Kostas' talk, because he was... Yeah, it's true. It's too late. So you can characterize MB-free pricings in multidimensional settings as well. And the characterizations look a lot similar. You have to be careful in multidimensional settings because if you have, like, say you did a combinatorial auction and you wanted to look at combinatorial auctions in MB-free revenue and combinatorial auctions, then if you do this trick where you sort of have an item that for each person, right? I have an item for player 1, an item for player 2, an item for player 3 that only they can get. And they have no value for anything unless they get their item. So they want to get their item and they want to get also some other stuff. Well, this kills MB-free approaches, because the whole point of MB-free approaches is I'm replacing incentive compatibility with some kind of symmetry constraint. And if I have these bidders who are highly asymmetric and if there's one item only they want, then I'm going to kill any kind of symmetry arguments and basically make MB-free prices way too strong, and so no IC mechanism can approximate them. But as long as, and you'll remember my, I don't know how to go back. You'll remember my main theorems looking at downward closed and make-twice settings. I did this kind of hybrid between Bayesian and worst case, where I said, assume I have worst case values, but let's randomly permute them with respect to the set system, the feasibility constraints, to get this symmetry that we want. So it's kind of like a secretary kind of approach. And you want to have a symmetry to take advantage of MB-freeness. And so probably these techniques that Kostas talked about, where symmetry was sort of inherent, you could try to do similar results with MB-freeness and show that things were close. I would guess something like that, but haven't thought about it at all.
Okay, let's take the rest of the questions offline. Thank you.
Jason, you're lucky you didn't have me as a session chair.
Yeah.
You don't want to broadcast this.
What do I do?
No, I mean...